Okay, I was about to ask.
Okay, so I'll talk about the frequency and time dependence of the polarization from blazars. I don't really have to cover this introductory material because previous speakers have done that. The observations that we'll be presenting are from the Perkins telescope in Flagstaff, Arizona, that the Boston University now owns and operates. We usually get R-band measurements on multiple nights each month whenever a source is visible. And occasionally we get multiple intranight 4-band measurements at I, R, B, and B filters. And so that will play an important role. We do VLBA imaging roughly monthly at 43 gigahertz, which also gives us polarization images of the jets. And then to interpret, use my TEMS computer model, where you have thousands of turbulent cells and the magnetic field, the turbulent magnetic field follows the Kolmogorov spectrum. The order magnetic field can be helical, can have other geometries as well, and that can be optionally added. And then also optionally, we can have a standing shock that has a shape of a cone, often called a recollimation shock that partially orders the magnetic field. Okay, so here is our observations of the well-known object BLAC. You see, this will be the same for all of the objects that I'll show. On the left-hand side, I have gamma ray light curve on the top, then X-ray light curve, then the R-band optical light curve, then the optical polarization at R-band, and the EVPA of that. In the middle, there were a time when we were able to get either intranight or internight observations of the polarization. And those nights are denoted by a red vertical line here. See, sometimes we got it during a flare, other times it wasn't during a flare. In any case, we're capturing a polarization variability either from night to night or during a given night. Then we have the VLBA image closest to the time when we had these very well-sampled observations. You can kind of see in concert with what Sebastian Kuhlmann said, that you have during the night-to-night, intranight variations, you can get quite substantial variations. And so the better time coverage you can get, the better off you are. You also can see that there are color dependencies, band dependencies in the polarization. The error bars are drawn here. So anytime you see, you can't see the error bar, it means the error bar is quite small compared with the data point. Now, these were not taken exactly simultaneously at the different bands. They're one band after another. And so some of the apparent variability from band to band can be time variability, but there is some color variability, which is an indicator of turbulence. Okay, for this object, during quiescent periods, we have the jet is EVPA in the optical is fairly stable. It varies by plus or minus a few tens of degrees, but fairly stable along the same direction as the EVPA of the core here in the jet. Here in the image, the black hole will be up to the north a little bit. During the flares, polarization can be, like during here, the polarization can vary quite erratically. So we have obviously some order going on, ordering the polarization parallel to the jet, so magnetic field predominantly perpendicular to the jet, but also a fair amount of disorder that is turbulence or something that acts like turbulence. This is the quasar 3C279. You see it has kind of two parts over the 10-year light curve. You have a time when really the polarization variability was fairly wild and the EVPA varied a lot. Then the EVPA didn't vary all that much. It kind of hung around plus or minus 20 degrees around the direction of the jet. Again, disorder superposed on order. And we have an intranight variability that is band dependent. Quasar 1156 plus 295. We caught it during an outburst in gamma rays, X-ray and visible light, and there was also a polarization outburst. You can see also the intranight variability. This is intra-night variability because it's all during the same night. The polarization you can see, the polarization, both degree and the EVPA, varies erratically across the bands. But the optical polarization that we observe here, the polarization position angle around 40 degrees, is very similar to what we see in the core. So it looks like that the variable polarization component is occurring in the radio core that we see in the 43 gigahertz images. So we presume that the core is highly turbulent. The quasar PKS 1510-089, the one that has had a lot of polarization rotations in the past, and you can see some going on here. You see that the polarization position angle actually varies quite erratically, as does the degree of polarization. So there's no stable optical polarization direction. During the flare here, where we caught it during an optical flare. During the flare, we see the optical rotation, but it's actually, you see that the rotation is different for the different bands. And so this really looks more like turbulence than it does some kind of physical rotation of the magnetized region. The position angle of the core polarization remains roughly stable during this period, both earlier and later and so on, but that appears to be unrelated to the optical EVPA. Okay, now going to interpretation, I just did some simulations where we look at the color dependence, the band dependence in the optical of the polarization. This is degree of polarization, the difference between the B band and the I band. This is the EVPA difference between the B band and the I band. See, when the polarization gets high, they tend to be fairly similar, although the higher frequency tends to have a somewhat higher polarization on average. But you see that it fluctuates back and forth, whether which one has a higher polarization. When you have no shock and no ordered field, then you get really substantial intraday variation. So this is just taking a 2-day period in the simulation, just some random 2-day period, and looking to see what the variations appear to be. And here we see that there is a band dependence and quite strong variability in the degree of polarization and somewhat in the EVPA. You can see some apparent rotation of the EVPA here.
3 more minutes.
Okay, thank you. And you can see how this changes as you change the degree or the fraction of the magnetic field that is ordered. Here's a 60% toroidal field and only 40% turbulent field, and you see that the variations are less severe, and that the band dependence of the polarization is different. See some more here. This is now adding a standing shock, and so you can see that there's more order to the polarization. There's less variability in that case. However, if you have a standing shock with the magnetic field being 100% turbulent before it goes across the shock, then you have more variations, both with wavelength and with time. Okay, if we take a look at the cases with a shock and without a shock, and with a helical magnetic field, different levels of helical magnetic field, we find that we don't have a shock, that there's not much of an association between the EVPA of the optical polarization and the direction of the jet. But if we do have a shock, then we have a good correlation between the direction of the EVPA of the optical polarization and the direction of the jet. It's not a perfect match, but it's much better correlation. So that's one way of discriminating whether you have a standing shock in the jet. And finally, looking at the BLAC object, Heraklion 421, where we did subtract, as it would be a LAC, we subtracted the host galaxy contribution to the polarization. Here you see the polarization varies up to around 15%. And the EVPA is quite variable, although it kind of varies by plus or minus 50 degrees about the same direction as the EVPA of the core in the radio jet. You also see substantial variations, night-to-night variations at different colors with some color dependence. So it looks like there's a fair amount of turbulence going on here, plus some ordering, maybe by a shock. So I modeled this with a TEMS model that includes a shock with a turbulent magnetic field flowing across it, and with a 50% helical magnetic field. So the field before it crosses the shock, it's 50% turbulent, 50% helical, and then see what we get in the optical versus the X-ray. And so this is the degree of polarization where the X-ray is in black and the optical is in red. And you see they're both highly variable as a function of this is, again, taking a 2-day random time within the simulation. And here's how the EVPA varies with the two. If we compare the optical and the X-ray, you find that, as some of the other speakers said with their models, is that you get that the average polarization of the X-ray is greater than that of the optical. But the EVPA tends to be fairly similar to the optical unless the polarization is quite low. Okay, so this variation that you get of the time variation that you get means that you have to be careful about the integration time. Fortunately, Marcari 421 is very bright in X-rays. So with IXPI that will be launching, we hope in late 2021, to measure the X-ray polarization, we think we can detect it on a fairly short time scale. So we can decrease the integration time and see if we get an increase in the degree of polarization. That will tell us that if we're kind of not resolving the time variability. Okay, so I'll just put up my conclusions, and which you can read. And thank you very much for your attention.
Thank you. Are there any questions? Please raise your hand. Go ahead, Vandan.
Yes, well, I have one. In the simulation, you show that, okay, so B, R, and I band. So, and well, is there any technicality, lack of the data in the B band, or there is some other explanation behind it to just select these 3 bands for the polarization?
Yeah, that was about as many frequencies as I could do, because I do frequencies all the way from radio to gamma ray, and I parallelized the program so I could do 64 frequencies. So those are ones that I selected. I don't think there'd be much difference between V band and R and B. So I just want to illustrate what the differences were among the bands. But yeah, it was just a choice that I made.